Hi, and today we're going to talk about a pretty interesting Algebra 2 topic, or at least one that kind of combines both algebra and geometry in function composition. That's right, we're going to be making functions. And how we're going to be making functions? Well, we're going to be forcing two functions and jamming them together and making a new, beautiful, unique, and distinct function. And as you'll see, this process is not always as straightforward as it may sound. I take one function, boom, I make it into another function. But before we talk about that, let's get into why and how we are able to make new functions out of jamming together old functions. We call this process, anytime we're taking two functions and making a new function, function composition, or composite functions. And the general thought process is this, right? Say I have one function f, right? I want to evaluate f. I want to be able to plug in a value at f, right? So I want to be able to plug in something here, and if we think about functions like factories, this is the metaphor I like to use, right? We imagine a factory line where there's this machine that performs a certain operation, and we'll call this machine f. Right, and so I put in, a toy or an iPad or some piece of machinery, and this function f, it stamps it, it packages together, it does something to it, and outputs a product. Right, it's stamped, it's packaged, it's wrapped, whatever. Right, well, function composition says, what if I take this modified object and I pass it in to another function, another machine. Let's say G, right? So it takes this already modified object and performs another type of modification on it, and then it outputs the further modified version of that, right? If you were to do it in a little bit more algebra-friendly terms, we'd say, right? Well, we take f of x, we put the output of that into G, right? So we have an input. We put it into f, we take that output, we put it into g, and our output, we would say, is g of f of x. In this case here, right, we plug in x into f. We get an output. We use that output as an input for g of x. We plug this whole f of x output into g of x, and that's our answer. And that's what we call function composition. That's the algebraic way. If you're ever stuck or confused, just think of it like a factory machine line. I've got one machine, it does one thing, it outputs a product. I take that other product and I feed it into my next machine, and that outputs my final answer. Right? Now, you may also see it written as G or composition of f of x, right? And this symbol basically means the same thing as g of f of x. You'll see this written a couple times depending on what textbook or learning resource or teacher you have, right? It's important to note this is a small circle. It's not a fill out dot. This isn't g. This isn't this, right? Because that would mean multiply. That'd be gf times x, which doesn't really make sense as a function. That's not what we're doing here. It's just a circle, which just represents function composition. I won't use it. I find it's a little cumbersome to use, and it's kind of confusing if you're not used to it. But you may see it written this way, and so it's just a good thing to put in your mind, just in case it ever actually comes up, and you ever see a problem that's like that. You don't freak out and say, "Oh no, what does that symbol mean?" It just means it's a composite function of this using this. But enough of all that. Let's actually do some composite functions, right? So let's do an example. F of x is equal to 2x plus 3. And let's say I want to find f of x. What am I going to do? Well, I say, I apply f, right? What do I get when I apply f? Well, my result is 2x plus 3. Okay, well then I need to evaluate f for 2x plus 3. So that's 2, right? Imagine that this is my variable, right? I take my variable, I multiply it by 2, and then I add 3 to it. So my original function, right, f of x is equal to 2x plus 3, right? If I apply that using x, if I plug in x here, I'll get 2 times x plus 3, 2x plus 3, right? I'll take it, I'll plug it in to f again, and so this whole thing, this big whole thing, is the same thing as my variable here. It's very important to remember because you can get tripped up when you just say, okay, this is 2x plus 3, and this is 2x plus 3. What am I going to do with that x, right? Because this isn't just x, it's 2x plus 3. Treat it as a variable. Don't get hung up on the variable name. Just think of it as a variable. Anytime I have a variable, I'm going to plug what's in my parentheses input, and I'm going to perform what I have to perform on that variable. In this case, I have to multiply my input, which is 2x plus 3, by 2, right? When I do that, I get 4x plus 9. And that is equal to f of x. Right? And so, if we look at what we did there throughout that whole process, we had an x, which we fed in as the input to 2 times the input plus 3. We took that result, we fed it into 2 times the input plus 3. So in this case, this is x. Result was 2x plus 3. We plugged that in as our input here. And the result was 2 times 2x plus 3 plus 3, right? And that's composite functions. But it's not always as simple as that. Sometimes you may be asked about domain, and domain can be a pretty tricky thing, right? So let's say I have, f of x is equal to the square root of x, and you might say, okay, if I was asked to use a composite function with this, I just take it and plug it in. Well, we have to be careful, because when we're using the square root of x, our answer, our output can't be a negative number, right? The square root of negative 4. What two numbers can I multiply together to get negative 4? It doesn't work. There's no answer. So our domain, our input here, right? Our input can't be negative. It can be 0, and it can be all the way up to infinity, but it can never be negative. Because if it's negative, we have a problem we can't solve, right? If I plug in negative 10, well, I'm not going to be able to find two numbers that multiply together to get negative 10, so I'm not going to be able to solve this square root. So I can't have negative 10 as an input. I can't have any negative number as an input to this function. So my domain of this function has to be non-negative. So how does that affect when we're doing composite functions? Well, let's say f of x is the square root of x, and g of x is x squared, and I want to find g of f of x. I'm gonna follow my process, right? I start with x. I'm gonna input that into the square root of my input, right? That's f of x, right? I guess let's just wait this way, all right? I want to take an input, plug it into f of x, and then take that output and plug it into g of x, and then find my answer. Let's break it down further. I plug in my x into f of x, which is just the square root of the input, which I output, right? And then I want to find the input squared. So in this case, square root of x is my output here. I'm going to plug that in, my input here, and I get square root of x squared. That's square root of x times square root of x. Let's just cancel out the square root, so I'm left with x. Right? So I say, oh, g of f of x is x. And if I was asked for the domain of this function, I'd say, oh, well, it's x. It could be any number. It can be negative 1 billion. It can be 10 billion. But no, and that's where it's tricky. We have to consider the domain of both of our functions, both the f and the g, not just our final result. Because for f of x, right, we can't have negative numbers. Negative numbers just won't work. So the domain isn't all the numbers. It's, once again, all positive numbers. So why do we have to consider both of the domains, right? Well, if we go back to thinking about functions as machines, right? If we plug in something that the first machine won't allow, right? If we plug in this case, a negative number, this first machine breaks, it explodes, it catches fire, things go crazy. It's not going to have anything to output, which means since the machine G does operations on the output of whatever F is, our machine G doesn't have anything to do. It can't do anything. It doesn't have a valid input because machine F, which feeds into it, is broke. So we're not going to be able to have a value of G of F of X. We have to make sure both, consider both our functions when we're thinking about domains. Make sure we're inputting values that are valid for both functions, because if they aren't valid for either function, it means our whole chain isn't going to work. Right? We have to make sure we can plug something in, it goes through the machine F just fine, it's valid, machine F is able to do what it needs to do, it's able to output something that machine G is able to take in and do what it needs to do, and then output our final product. Now, lastly but not least, we have graphical composite functions. You may often see graphs and be asked to find values based on composite functions. So we have our coordinate plane here. And let's say I have a graph like this, which I'm going to say is g of x. I have a horizontal line that I'm going to say is f of x. And I'm asked, what's f of g of 8? Right? Well, let's think about our assembly line here. We have 8, which we're plugging into g of x. We're going to take that value, and we're going to plug that in for f of x, and we're going to get our answer. So, we plug 8 into g of x, right? So I'm looking for the y value when I plug in an 8 for x. So let's say I'm at 8 and I say, oh, it's 2, right? So my output, a g of 8 is 2. Right? Well, I'm going to take that 2 and I'm going to plug it into f. So I'm looking for f of 2. And so okay, where's f2? And I say, oh, well, that happens to be -3. Right? That means my answer then is -3. So when you're dealing with graphical composite functions, when you don't have your equations or your formulas, you're going to look at your x, right? Find out the y value for that first function inside that parentheses using that x value, right? So just look at the graph. Find that corresponding point. You're going to take that in, and you're going to use it as an x value for your next function, right? So I'm going to take that new y value, right, and basically use it as my x value for this one. So I'm going to look and say, okay, 2. What's my y value when my x value is 2 for f of x, right? So I start out with an x value. I find the corresponding y value. And then I find the corresponding y value for the other function using my previous y value as an x value. Now that all sounds confusing. Just think back to this progression, right? Start with our 8, right? Find out what we get when we plug 8 into g of x. We use that, we plug it into f of x, and we find out what we get when we plug that into f of x. And that final step is our answer. So just don't get caught up in individual functions. Don't get freaked out. Just remember, I have my formula, I have my assembly line, I have my process. I'm going to use my assembly line. I'm just going to look at the graph, and everything's going to be okay. It's important not to psych yourself up, because if you do that, it can be pretty difficult. Just remember, I've got this. I know the process. I don't need to do anything crazy or fancy. And that is composite functions. You have successfully mastered it. I hope this video helped you, and I hope you have a great day.